Hi, this is Ryan, and I'm going to talk to you about the Racket database library, a problem that it has, and a new feature that Racket on ShaScheme offers that helps us solve the problem in a better way. Okay, the Racket database library has two kinds of connections. There are wire-based connections that implement the database wire protocol and just use ordinary Racket I/O to talk to the database server. The other kind of connection is FFI based. We use the Racket FFI and the corresponding native library to communicate with the database. So examples are SQLite, where we use the SQLite library, and ODBC connections, where we use the ODBC library, where we can communicate with anything that we have an ODBC driver installed for. So why does the kind of connection matter? So we need to talk about Racket threads. Racket threads are green threads. That is, the entire Racket VM runs on a single OS thread, and Racket implements its own notion of threading on top of that. The Racket thread scheduler cooperates with the I/O and event systems. And this means that since wire-based connections just use ordinary Racket I/O, wire-based connections work perfectly with the Racket thread scheduler. For example, if you have a wire-based database connection that blocks doing I/O, the Racket thread scheduler can allow another Racket thread to run while it waits for this I/O to complete. What about FFI-based database connections? An FFI call blocks all Racket threads until the FFI call completes. So for example, if you have an ODBC connection that executes a query, it's going to call SQL execute. That FFI call might involve talking to a server, sending a query over, waiting for the server to do some computation, and then sending the result back. And the entire Racket process cannot perform any actions while it's waiting for the FFI call to complete. And so this is the fundamental problem with FFI-based database connections. They can degrade the responsiveness of the entire Racket process that they're running in. So how do we fix this problem? The old fix is to run the query in a separate place. A place is essentially an entire Racket virtual machine instance that runs in a separate operating system thread. It has its own threads, it has its own scheduler, it has its own memory and garbage collector. The original place, when we use the place fix for this issue, the original place will have a proxy database connection. When we perform a query, it sends the query over to the other place, the database place, and runs the query in that place. Meanwhile, this thread is blocked waiting for a response from the database place, but the Racket thread scheduler can run other threads in the original place while it's waiting. This FFI call blocks all threads in this place, but this place isn't doing anything else besides running database queries anyway, so it doesn't matter very much. Right? When the FFI call completes, the database place serializes the results and sends them back to the original place. Remember, there is no shared memory, so we have to send this as a message. It sends them back to the original place deserializes them, and then continues computing. Right? So this fixes the responsiveness problem, but what is the cost? So there are two kinds of costs. We have the memory overhead of creating a new Racket virtual machine instance, which I don't have numbers for, but is going to be in the megabytes, if not the tens of megabytes. And we have the time overhead particularly because of this serialization step. And so using the Racket database library test suite as a benchmark, the time overhead is about 100%. That is, the tests take twice as long to run compared to the original implementation where we just run the FFI call in the original thread and we accept the loss of responsiveness. So this solves the problem, but it's a bit costly. Can we do better? In Racket on Shea Scheme, we can. So Racket on Shea Scheme gives us this new capability of creating an OS thread without the overhead of creating an entire Racket place. The structure of the solution is still about the same. We have a proxy object here. When we perform a query, it sends it over to this database OS thread, not place, but just simple OS thread. The OS thread performs the query, including any blocking FFI calls, and then sends the results back. We no longer have the overhead of an entire Racket virtual machine instance. We no longer have the serialization overhead because this new operating system thread is in the same shared memory space as the original place. And so we eliminate the serialization overhead. On the other hand, this is still outside of the place, so it can't use certain features like the thread scheduler, the I/O system, and so on. Okay, so let's look at the cost for this. We no longer have to allocate a new Racket virtual machine instance, so the memory overhead is minimal. The time overhead drops to about 20% instead of 100% because we've eliminated the serialization and deserialization steps. On the other hand, since we're running this code outside of the Racket virtual machine, essentially, there are restrictions on the code that we're allowed to run in an OS thread. So let's talk about those restrictions. Racket code running in an OS thread cannot use continuations, including exceptions. It can't use synchronizable events, including channels for communication. It can't use Racket threads, parameters, it can't perform I/O, and so on. And the solutions to these are relatively straightforward, but involve touching a lot of code. So for the exceptions, in some cases we just fall back to writing the code in monadic style instead, using an error monad. And then at the end, if we had an error, then we wait until we return to normal Racket mode to raise the exception. Instead of channels, we use OS async channels that are designed to communicate between Racket threads and OS threads. And this channel also handles the memory fences that are necessary when you're communicating between OS threads in a shared memory space. So this takes care of that. All right, and then there's also some complexity with disconnecting now, especially in response to a custodian shutdown. Essentially, we do part of the disconnecting in the OS thread so that we don't disconnect while the OS thread is actually doing work and using a connection. So in summary, Racket CS gives us this new feature where we can run restricted kinds of Racket code in OS threads, and this helps us solve the responsiveness issue with FFI-based database connections with lower overhead than the previous solution. I've added support to this to the database library since release 8.0. This is now the default behavior if you're running on Racket CS and you use usePlaceTrue for SQLite 3 Connect or ODBC Connect. So if you use either one of those, then please help me test this for the 8.1 release. Right? That's it. Thank you very much.